Imagine someone hands you a few playing cards. How do you sort them? You look at each new card, find where it belongs, slide the bigger ones over, and drop it into place. You don't even think about it. It just feels natural. Well, that thing you just did. That has a name. It's called insertion sort. You take each new element and you insert it into the right spot in the sorted part. That's it. That's the whole algorithm. Now it's an n-squared algorithm, and usually n-squared means slow. But here's the thing that makes insertion sort different. This is the algorithm that Python actually uses inside its sorting, and C++ uses it too. So how does a simple n-squared algorithm end up inside the world's fastest sorting systems? This is insertion sort. Let's find out. Here's how we think about it. We imagine the array in two sections, a sorted part on the left and an unsorted part on the right. At the very beginning, the first element is already in the sorted section. A list of 1 is always sorted, right? So, we move to the first unsorted element. We pick it up. Let's call this our key. Notice how this leaves a temporary empty space in the array. Now, we just need to find where this key belongs in the sorted section. We scan backwards from right to left. If we see an element that's bigger than our key, we shift it to the right to make room. We keep sliding bigger elements over until we find an element that's smaller than our key, or until we hit the very front of the array. That's the perfect spot. So we just drop our key right in. And just like that, our sorted section has grown by 1. But here is the real magic. What if the data is already mostly sorted? When we pick up the next key and look to its left, it's already bigger than the element before it. Because it's already in the right place, we don't have to shift anything at all. We just put it right back. This is why insertion sort is incredibly fast, when your data is already almost in order. Now let's read the pseudocode. Line by line, we start with a function that takes an array, and we grab its length n, the outer loop. Notice, we start at index 1, not 0, because a single element is already sorted. Index 0 is our starting sorted section. Now, this line is critical. We save the element at position I into a variable called key. Why? Because the next step shifts elements into this slot. If we don't save the value first, it gets overwritten. Gone. Save the key first, always. We set j to I-1. That points at the last element of the sorted section. And this is where we start scanning backwards. Lines 6 and 7, the heart of the algorithm. While j is valid and the element at j is bigger than our key, shift it 1 slot to the right and step j left. Watch, key is 1. Sorted section is 3, 5, 8. 8 bigger than 1, shift. 5 bigger, shift. 3 bigger, shift. J fell past 0. Stop, each shift is just 1 right. The gap travels left as we go. One important detail, the condition uses strictly greater than, not greater or equal. That's what keeps this sort stable. The loop stopped. The gap is at j plus 1. Drop the key in. And watch out. It's j plus 1, not j. That off by 1 is a classic bug. Sorted section just grew by 1. That's the whole algorithm. Save the key. Shift bigger elements right. Drop the key into the gap. Repeat until done. Let's run the full array. 6, 5, 3, 1, 8, 7, 2, 4. Index 1. Key is 5. Compare to 6. 5 is smaller, so shift 6 right. End of the sorted section. Drop 5. Index 2. Key is 3. Compare to 6. Smaller, shift 6. Compare to 5. Smaller, shift 5. End of the section. Drop 3. Index 3. Key is 1. Compare to 6. Smaller, shift 6. Compare to 5. Smaller, shift 5. Compare to 3. Smaller, shift 3. Drop 1. Index 4. Key is 8. Compare to 6. Wait, 8 is bigger? Stop. Drop 8 right back where it was. Index 5. Key is 7. Compare to 8. Smaller, shift 8. Compare to 6. Bigger. Stop. Drop 7. Index 6. Key is 2. Compare to 8. Smaller, shift 8. compared to 7, smaller shift 7, compared to 6, smaller shift 6, compared to 5, smaller shift 5, compared to 3, smaller shift 3, compared to 1, bigger, stop. Drop 2, index 7, key is 4, compared to 8, smaller shift 8, compared to 7, smaller shift 7, compared to 6, smaller shift 6, compared to 5, smaller shift 5, compared to 3, bigger, stop. Drop 4, done. Final count, 20 comparisons, 16 shifts, much faster than Bubble Sort's dry run on this exact same array. Let's talk about complexity, time, and space. First, the worst-case scenario. Imagine an array in completely reverse order. Every new element is smaller than everything before it. So it has to walk past the entire sorted section, shifting every single element. If we map these comparisons on a grid, element 1 does 1 check, element 2 does 2, element 3 does 3. You can see the pattern building. It forms a triangle, covering exactly half the grid. This is why the worst-case time is O of n squared. But insertion sort has something special. It is adaptive. Watch what happens if the array is already sorted. The next element looks at its left neighbor. It's already bigger. So it just stops immediately. 0 shifts. On our grid, the work shrinks down to just this single diagonal line. 1 check per element. In the best case, insertion sort runs in O of n time. What about space complexity? We only need 1 extra variable to hold the key, so the space is O of 1. It sorts entirely in place, and stability, because we only shift when the sorted element is strictly greater than our key. Identical elements never cross each other. So yes, it is a stable sort. Finally, let's compare it to bubble sort. Both are O of n squared, so why is insertion sort used in real-world libraries? Like Python and Java, it comes down to memory writes. Bubble sort uses swaps. Every swap is 3 memory writes. Insertion sort uses shifts. Every shift is just 1 write, same mathematical time complexity, but a fraction of the physical work.